saying, okay, I've done this multiple times and I was only able to get the correct answer once, so let's go. Okay, basically the first thing, whenever I know they say to like compute this, but the first thing that we have to do is check if this field is conservative. Okay, field force, yeah. Okay, so basically check and how do we check if this is conservative, right? The way you check is you have to check if the curl is 0. And the curl is defined by the gradient crossed with the function, right? And we have to check if this equals to 0. So basically, this thing right here is our P, this thing right here is our Q, and this thing right here is R, okay? And basically, how do I say this? Okay, yeah. So basically, we have to, the gradient is just like the partial derivative of each of these P, Q, and R, okay? But you can do the cross product in terms of the determinant. For me, I like to do it like in high school. I was taught like in a way where you just like write out and you just cross like that. So I'm gonna do. It's easier for me. I don't know, to compute. So basically, what we have is okay. In general, like what you would have is like I, J, K, and you would have del X and del Y, del Z, and then you have P, Q, R. And you just take the determinant of this, like this, sorry, like that. I don't know, I like to do it the way I learned it, which is just, you just write this, then this, in a line. So, sorry. I'm gonna do that. So basically we have del, I'm gonna write it here. We have del Y, del Z, del X, and del Y. And then we have Q, R, P, Q. And we're gonna just go boom, boom, like that. So this side, it'll be del R, del Y, minus del Q, del Z, plus, so this is the X component, okay? Then we have del P, del Z, minus del R, del X, okay? Then we have this, del Q, del X, minus del P, del Y. Okay, so that's our cross product right here. So this part is, this is X, this is Y, this is Z, okay? And basically we're gonna see, does it equal to 0? And if it's a 0, that means it's conservative. Okay, so basically the reason we're checking if it's conservative is that, what is it called? You can, if it's conservative, you can write this function right here as the gradient of something, and then once you do that, what you can do is like you have some endpoint, and you can subtract it from the beginning point or whatever it is, and basically whatever you get here is going to be the answer of this. That's why we're like checking if it's conservative, because that gives us an easy way to solve it. It's not easy, but like a way to solve it that like we know. Okay, so let's see. Okay, so we have to look at our R. So R is this thing right here, and we have to take the partial derivative with respect to Y. Okay, so let's do that. I'm just gonna do something. Okay, so copy. Okay. Alright, so this is going to be del r del y. So with respect to y, this is 0, this is 0, this turns to 8. So 8. Okay, just gonna erase this. Just gonna put this minus. Now we need del q del z. So it's this thing right here. And we need it with respect to z. So this thing right here goes to 0, and this one just turns to 8. Okay, we can already see that this is the x component, right? And we say that x is equal to 0. And then we have, what is it, del p del z. So it's the same thing. No, sorry. Never mind. Ignore what I said. So it's del p del z. This one right here, we have to take it with respect to z. Right? So that is going to be, this whole thing goes to 0 because there's no z in it. And this one, you do the power rule, becomes 18 z to the 5, right? Okay. Then we have minus. So what we did this, and we just did this. Now we need to do this, which is dr dx. So we have to look at this thing right here. And we have to differentiate that with respect to x. Okay, so what would that be? This one, we have an x here, so that just goes to 1. And so it becomes 18z5. This one is 0, and this one is 0 as well. So it's just this. And again, we can see that this is our y component, and it's equal to 0. Okay, and then we have dq dx. So that's this. Okay, so we want to differentiate that with respect to x. Okay, first thing you can say that this goes to 0. This one, you can just do the power rule. So it would be 8 times 9, which, why my brain is not working? 72, yes. 72 y x 8, and then this is divided by, nothing changes, right? Y squared plus 6. Okay. Erase this. Fix this a little. Okay. Okay. And then we have minus. This is our final one. So dp dy. So it's this thing right here. Sorry. dp dy. Okay, we have to take this with respect to y. Okay, so again, this goes to 0. This one, I always forget this, but basically this, if you differentiate it, it just becomes like ln x is 1 over x. So this thing is technically like an x. So this just goes to the denominator. And yeah, okay. And then you multiply, it goes to the denominator, but you also have to multiply by the derivative of the inside. Okay, so basically, what happens is you have, again, the denominator, so y squared plus 6, and then if you take the derivative of this with respect to y, it will be 8y, and then basically we have this 8 and this 9, so that becomes 72, and it's x to the 8, and then we just have a y, right? And again, this turns to 0. So in like reality, everything is 0. So this is true. I know like this question technically, because it asked us, like you can kind of, I don't know, if it's not, like it's a question asking us to compute something, and I don't think we know any other way to actually solve this. I think if it was like an exam or like a test, you can just assume that it's conservative because it takes so long to just compute this, but yeah. Yeah, you could have just started off by assuming that it's conservative because like there has to be an answer, but yeah, this just proves that it's conservative. Okay, now this means that what this means is that you can write this f as some gradient of phi, and what we want to do is solve for what this phi is. Okay, but before I do that, actually, just to kind of make our life a little bit easier for later, what I'm gonna do is, so we have this endpoint, okay, we have this endpoint and this starting point. So what we can do is just compute r at t, because I know, like I said this before, when we solve, we're gonna have like something like this, right? And to get whatever that point in the middle is like with these endpoints, right? So what I'm gonna do is just like compute those endpoints, because it's just like the easiest thing we can do right now. So let's do that. Compute, like basically like starting and ending points. So basically let's do r at 0. So r at 0 will be, it's just a parameterization as well. Okay, so that's okay, so it's t cubed. Okay, one mistake that I made earlier is that I added it's kind of funny. I just took like whatever this is, and this is, and added it, but actually it's actually coordinates. Just like don't make that stupid mistake. So yeah, okay. So if you have r at 0, it just becomes 1 for x. This one becomes 2, and this one is just 0. Okay. R at 1. So that would be 1 plus 1, which is 2. 1 plus 2, which is 3. And this one's just 1. Right? Yeah. Okay. So, yeah, this will not now, but come in handy at the end. So, just gonna highlight this. We'll come back to this. Okay. Now is where the hard part comes in. Okay. So, yeah, we have that f is going to be equal to some gradient of phi. So we can say that f, so basically f is this thing right here, whatever, like in coordinate form, it's just p, q, and r. So I'm gonna like just rewrite that in coordinate form because it's much easier. So this is our x. Just fix it. Sorry. Can you tell I'm lazy? Okay. Okay, so this is our x, and then our y is this. Sorry. Okay. And then our z is this thing right here. Okay, Okay, so yeah, this is our coordinate. I'm just gonna separate it a little bit because it can be confusing. So this, this, and this. So this is x, this is y, this is z. Okay, so by definition, we also know that this gradient of phi is going to be del phi del x del phi del y and del phi del z, right? And again, we said that here these two are equal to each other. So what you can do is, again, they're both coordinates, so what you can do is just equate the components. You see how these are equal, these are equal. So what you can do is you just start off with this and you set them equal to each other. So we have del phi del x is equal to 9x to the 8 ln 4y to the squared plus 6 plus 3z6. Okay, that was the whole x coordinate. Now what you do is you have to take the partial integration. We've never even talked about this, but it's like a new concept. Okay, so that's to get phi, right? And this phi is with respect to x, y, and z. Okay, so that's the integration of 9x 8 ln 4y squared plus 6 plus 3z6. And then it's just dx. So basically, because this side is like kind of you're like technically this is the derivative with respect to x, we have to integrate with respect to x. And kind of, I don't know if this is the right way of thinking about it, but I think about it like this. Basically what's happening is you bring like just I don't think you can think of derivatives as like multiplying, but I just take this and I multiply it here, and then we have like the derivative of this. In order to get the derivative or just this, you just integrate, and that's why it becomes this. That's just how I think about it. Okay, so what is this? Again, we're doing it with respect to x. So this thing right here, this is a constant and this is a constant. This thing is the only thing we're worried about. So if you integrate this, we get x, you add 1, so that's 8 plus 1, which is 9, and you divide by 9, so this thing actually like cancels out, right? So we get x to the 9. Again, this is constant, so we're just gonna leave it like that. Plus 6. And then here we just have a constant, so we just add an x. Okay, and then also another very important thing is our constant. So whenever we take integration, right, especially if it's, I think, a definite integral, we have this constant c. But because we integrated with respect to x, we can assume, because we have to kind of like test all the possible solutions, right? So we can assume that the function or the constant is a function of y and z. So let's say like this. Okay, so we're almost there. The pesky constant is the only thing we have to worry about now. So this, what do we do? Basically, all we did so far is compute this. Compute this and this. We still have these two and these two. So, what you can do is now do this and you do this. Again, this is kind of like I think of it like magic, because like, I don't know, it's hard to like actually realize this, but okay, so basically what we have right now is this, and right here you see this thing right here. If you take this and you differentiate it with respect to y, then whatever we get for the differentiation is going to be equal to this, and this thing right here is equal to this, right? So we can take the partial derivative of this, and then we can set it equal to this, and hopefully it'll help us to see if the constant depends on y. And if it doesn't, then we have to check with respect to z, and then if it doesn't with that either, then it's just like a scalar constant. Okay, so basically what we're doing is like unintegrating this, but with respect to y, not with respect to x. So we get this. So del, I'm just gonna write it like this because it's easier. Okay, del phi del y. So that's just the derivative of this with respect to y. So right here we have this thing, it's trapped inside of here, and the derivative of a ln, pretty sure is 1 over x. I'm pretty sure I said this earlier. Sorry, I'm just gonna, yeah, it's 1 over x. Okay, so let's go. Okay, so if you look at this, it turns into x to the 9 over 4y squared plus 6 right. Okay, yeah, and then we have to take the derivative of this and multiply it, right? So that's 8y. That's it. The 6 disappears. This thing right here disappears because there's no y, and this just becomes g prime. Right? Okay, so like I said earlier, now what we can do, this thing is equal to this, which is equal to this, right? So we can compare them. Okay, so basically we have this. I'm very lazy, I'm sorry. Okay, so we can see that this thing right here and this thing is the same, this thing right here and this thing is the same, so we cross that out, and we get that our g prime at y comma z is equal to 8z. Now what do we have to do? Okay, also remember, this is with respect to like y, right? So we have to integrate, but with respect to y. So g at y comma z will be this 8z dy. Okay, don't mess that part up. So because this is just a constant, you can just add an 8 z. I think I know where I made a mistake. Okay, earlier like I got stuck at this point, but I think I know now. Okay, so yeah, it's 8z y, right? And again, this is an integral, so we need some constant, and I think what you can do now is what is it? Now we have some constant again, but this constant is going to be with respect to like z, sorry. So this thing right here. Okay, so that's our g at y comma z. So what I'm gonna go do now is take this and I'm gonna plug it back, because we just have our constant, right? We can go back and we can plug it into here and this original equation. So we get It's a lot of work. And I just like took up a whole page. Yikes. Okay, I think I have to, sorry. Just add a page. Okay, so. Okay. We have this, and we have that our g at x is this thing right here. Okay, so now, so now we need to figure out what this thing is. So annoying. So this thing, so what we can do is, again, this time differentiate with respect to z, and when we do that we get this, which is equal to this, and then we can set them equal to each other and solve for what this constant is. It could be either a function of z or a constant number that, like, we don't really care about. Okay, let's go. So let's differentiate this. So we get del phi del z, so that will be so this thing is just a constant, so that disappears. This thing is not a constant, so that stays, and this thing stays as well. Okay, so this one right here will be 18 z to the 5x, right? Yeah. And then this thing right here is just going to be 8y. Okay, and we have h prime at x, right? Okay, oh no, not x, sorry, z. Okay, so now we can take this and compare them. So just gonna okay, so we have this and this thing right here, and we say they're equal, and we can see that this cancels, and we are left with h prime at z is equal to minus 4 pi sine pi z. Whew. Okay, now what we have to do is integrate with respect to z, right? So okay, what is this? So when we go backwards, it goes to cos, so this is positive, right, because it's going backwards. And so I'm gonna write that. So 4 pi cos pi z, and then what you do is you divide by whatever's inside, like the derivative of it. So this is just pi. Okay, so okay, I think we're left with the constant, but this time it's an actual scalar constant, but we also have to deal with this. Okay, so this is actually going to be the main difference for all the reasons why I got it wrong. I really hope I didn't make a mistake, because it's gonna suck. I think it's probably already been like 30 minutes. Okay, so we have that. I'm gonna write this in red because it's important. Phi at x comma y comma z is equal to, so originally what did we have? Okay, it was here, this thing. Okay. How did I write so unevenly in terms of a straight line? Okay. Okay, so, why did I change it black to, so annoying, okay. And then this H at Z we said is this. If this is an actual test and you have to write down all of this on paper, I'm very sorry. And I don't think they will ask this question on a test because of how long it's taking. Okay, so this right here is our very final potential function. Wow. So to get our final answer, what we have to do is take phi of something minus phi of something, and this something is the end point and starting point. So what's our starting point and what's our ending point? So our starting point, or sorry, it's end point minus starting point, so it's just this. Our ending, 1 second. Okay, so we had this here. So this is our ending point, right? So that would be 2, 3, 1. And our starting point was 1, 2, 0. So now what we do is just plug everything in. Okay, so let's do this step by step. Okay, so okay, so our x to the 9 is 2 to the 9 ln of 4, y was 3, so 3 squared is 9, 9 times 4 is 36, 36 plus 6 is 42, sorry, just let me ln of 42, plus 3, our z value is 1, so z to the 6 is 1 times, so we have 3 times 1 is just 3 times x, which is 2, which is going to turn to 6. Okay, plus 8zy, so z is 1, y is 3, so that's 8 times 3, which is 24. And then our final thing is 4 pi, that annoying thing. So, what is it? Cos, okay, z is 1, and I think it turns to cos pi. Cos of pi is negative 1. So, okay, I actually should have simplified this here. This pi and this pi cancels. So, that's just negative 1 times 4, which is negative 4. And we have this plus c. It's going to disappear. Okay, that's this thing is this thing right here. Okay, so we have this minus, now we need to do the second part. Okay, so what's this? We have x to the 9, x is 1, so just 1, ln of y squared, so that's 2, 2 squared is 4, 4 times 4 is 16, 16 plus 6 is 22, so that's gonna be ln 22, I think. Plus z is 0. Okay, wait, actually, I just simplify this a little bit. This is 0 because there's a z. This is 0 because there's a z. For this, z is 0. Cos of 0 is 1, right? So it's just gonna be 1 times 4, which is 4. And then plus c. Okay, that one's much easier and very nicer. Okay, so we have this and this. Okay, now, what is 2 to the 9? I have no idea. That's 5, 1, 2, ln 42, all these constants is 6 plus 24 minus 4 is 26, plus c. Okay, I'm sorry, just like the c annoys me. You can just look at it like this. this c is adding, you're subtracting the c, so it just turns to 0. So technically, like, you can just cancel that out. Okay, then what we have is minus ln 22 minus 4. That's it. And I'm just gonna combine these for this. The last thing we can do is just combine this and this. So it's 5, 1, 2 ln 42, and then yeah, just gonna write it ln 22, and then this and this is gonna end up being 22, right? No freaking way. That's the answer. That is the freaking answer. Ah! No joke. What the heck? I did this like 3 times. And that's crazy. Good job. I have no words. That's crazy. Good job.